Hello everyone, this is the second tutorial of our course Linear Algebra. So today I will discuss about basis, dimension, and first of all linear independence. Okay. So what is the meaning of linear independence? In previous day we discussed about generating set not generating, it is called spanning set. A set v1 okay, v1 v2 up to vn, the span of these vectors, it is given by this collection combination, linear combination of c1 up to vn, v1 up to vn, that is c1 v1 plus c2 v2 up to cn vn, and those ci's are belongs to the field of the corresponding vector space. So what is vector space? Vector space means it is a set with some operations, vector space over a field F. So vector space means it already equipped with two operations. One operation is called addition, which is a binary operation on V. Another operation is scalar multiplication, which takes a scalar and a vector as inputs and give us another vector. So the scalar act as scaling of this of a vector. Okay. So let us see an example. So as usual, if we consider R2, then R2 is spanned by those two elements, E1, which is given by 1 0, and there is another vector called E2, which is 0 1. Now we can say any vector, take for example pi comma e, something like this, or not don't make it complicated. So take 2 comma 3. Then what we do, it will, so we just go 2 times in the direction of e1. So that first it was e1 and then take another e1. So this is 2 times e1, and plus we'll go 3 times in the direction of e2, this, then this, and another. So the resulting sum, this will give me 2 comma 3, so 2e1 plus 3e2. Okay, similarly if we take all the other combinations, we'll get the whole plane, whole R2 plane. So this is how linear combination works. It lies something like at this place, and this is the definition of span. So instead of writing in this way, we also can write, take S as v1 up to vn, this set, then we can say span of S equal to this linear combination of all those vectors. Now what is linear independence? Suppose there are some vectors v1 up to vn. then those, again we are considering a set, subset of vector space V. Those will be called linearly independent. V1 up to Vn are linearly independent, or the set is linearly independent set. Independent if we take any combination, suppose take the combination C1 V1 plus C2 V2 up to Cn Vn. If we take this combination, and if this is 0 for Ci belongs to Ci belongs to the field, Ci, this equal to 0 implies all those Ci are 0 for all I. Okay, I equal to 1 up to n. So it says those will be linearly independent if 0 does not have any other representation than the trivial one. So 0 can be only if V1 up to Vn are linearly independent, then there is only one such representation, some C1 V1 non-trivial, that is 0 only can be written as 0 V1 plus 0 V2 up to 0 Vn. That is only the coefficient 0 is allowed. If we take any non-zero scalar entries, scalar as coefficient, that then the combination must give me some non-zero vector. So this is the definition of linearly independence. So then what will be the definition of linear a set is called linearly dependent if there exists some non-trivial combination. So V1 up to Vn, suppose instead of Vn, let us consider V1 up to Vn. Suppose this is a set, then this is called linearly dependent if there exists some V. Instead of V1, we take some choices from this set. So we don't need to consider all those sets, or otherwise what we can say, there exists some coefficient Ci non-zero, Ci belongs to field F such that C1 up to Cm, those are non-zero element. This is not equal to 0, not equal to 0 0. There exists some non-zero combination. There is Ci with this such that C1 V1 plus C2 V2 up to Cn Vn equal to 0. So this means there is some non-trivial combination which will give me the 0 vector. No one is joining today. Issue. Okay, probably there is no issue. Let us continue. So the definition of linearly dependence is that there are some non-zero combination which gives me non-trivial combination which gives me the 0 vector. Okay. So let us consider some example. For example, if we consider the previous one, then we can see that 2 comma 3, let us consider this vector as v3 and v1 equal to 1 0, v2 equal to 0 1. Then the set v1 v2 v3 is linearly dependent. Why? Because we can see that 2 comma 3, the vector 2 comma 3, this can be written as 2 times v1 plus 3 times v2, and this is nothing but v3. So this means, so v3 is actually dependent on v1 v2. On the that is equivalently we can say 2 v1 plus 3 v2 minus v3 equal to 0. So we can see the coefficient of this v1 v2 v3, not all of, in this case all the coefficients are non-zero, but I am saying it is enough to have at least one coefficient which is non-zero, giving me a zero vector. Okay, so this is an example. Another obvious example, if we take the zero vector only, this is, sorry, s equal to zero vector. Zero vector means in this case r2, 0 comma 0 is the zero vector. So this is always linearly dependent. Why? Because you can see 0 can be written as 0 times, sorry, not like this. What is my definition? C1 C2 of, okay, 0. So let us choose this as, let me give the name v. So 0 can be written as 1 times v. So we can see we have some non-trivial combination. 1 is non-zero, but 1 times v give me 0. 1 is non-zero, but 1 times v equal to 0. Therefore the set S is linearly dependent. Okay, we can consider lots of other examples also. So let us try to solve some problem and we'll see some non-trivial examples. Before that, let me give the definition of another important concept, which is called basis. So let S be a set, linearly independent set, that spans V. Then S is said to be a basis of V. So we have already seen that E1, E2, those are linearly independent. Why? Let us see why those are linearly independent. So if we try to make a non-trivial combination which is 0, so C1 V1 plus C2, so here the name is E1 E2, so C1 E1 plus C2 E2 equal to 0, that imply C1 times 1 0 plus C2 times 0 1 equal to 0 vector. 0 means 0 vector, but the left hand side is nothing but just component wise addition. So this is C1 comma C2, so C1 comma C2 equal to 0 0, that says C1 equal to 0 and also C2 equal to 0. So we don't have any non-trivial combination. If we try to make a combination which gives me 0, then that must imply C1, C2 both are 0. So from here we can see that E1, E2, those are linearly independent vector. Okay. And it is also clear that if we take any element x comma y, this will be x times E1, x times 1 0 plus y times E2, y times 0 1. So from here it is clear that that E1, E2 not only those are not only linearly independent but also spanning set for the vector space V. So E1, E2 will be a basis. Let me, so S equal to E1 comma E2, this set is a basis for R2, for the vector space R2. Now can we give any other basis? So let us see if it is possible or not. Let us consider instead of E1, E2, let us consider V1 equal to E1 plus E2 and V2 equal to E1 minus E2. E1 E minus, so it is actually 1 comma 1 because 1 0 plus 0 1 1 comma 1 and this is 1 comma minus 1. Now are those linearly independent set? So example 2 is V1 V2, this set a basis for R2. So first we need to see if those are linearly independent or not. So let us try to prove this. Answer. Let C1 V1 plus C2 V2 equal to 0. That will say V1 means 1 comma 1, so C1 times 1 plus a comma C2. So C1 times the second component is C1 times 1 1, so means the components are C1 comma C1. Now C2 comma 1 minus 1, that means C2 and the second component is minus C2. So this is 0 0. That means C1 plus C2 and the second component is component wise addition C1 minus C2 equal to 0 0. So that is same as saying C1 plus C2 equal to 0 and C1 minus C2 equal to 0, right? So note that those two are linearly independent equation. Why? Those are independent equation because if we write it as matrix, then it represent the vector 1 1 1 minus 1 into C1 C2 equal to 0, and rank of this matrix is 2, right? Why? Because if we just row reduce it, then this will be 2 comma 0 0 comma 1 minus 1 and again, so 1 minus 1, what we have done, R1 plus R2, right? Added R2 with R1 and then half of R2, let me do half of R2, that operation. So this give me 1 0 1 minus 1 and then R2 minus R1, half of R2, and also let us do the operation half of R1, sorry, minus R2. So it is minus 1 comma plus 1. Then let us do the operation R2 add R1 with R2, so it will give me 1 0 0 1. So those two are clearly now rank of this coefficient matrix. Rank of this and these are same because we have only performed some elementary operations, elementary row operations. Therefore, rank of this matrix is 2 because there are two linearly independent vectors. It is very clear. Those two rows cannot be dependent by the same kind of reason. So from here, we also know that if we row reduce, then the new equation from here, the new equation will be like this: C1 times C2 equal to 0, because row reduction always give us the same equation. So the solution of the previous equation is same as solution of the row reduced equation of the row reduced matrix. If we take coefficient matrix, this as a coefficient matrix, then a times this C equal to 0 is same as the row reduction form. So it is R, row reduced echelon form. Let me denote it by R. So AC equal to 0 if and only if R times this C equal to 0. So we are trying to find this C. From here it is clear that C1, C2 both are 0, because this equation implies C1 equal to 0 and C2 equal to 0. Right? So this, from this combination we get C1, C2 both are 0. Therefore, the set S is linearly independent. Now we check if it is a basis for R2 or not. Okay. What we can do? So if it is a basis, then any element x comma y can be written as some, I want to say, if is v1 comma v2, so v1 is 1 0, or sorry 1 1, v2 equal to 1 minus 1, is a basis, is a spanning set of v, then any element, choose any v equal to x comma y belongs to R2, this always can be written as combination of those two elements. So sorry, I have written as row, but now I am writing it as a column. But column notation is very useful because we don't need to, for example, here what we have done, see that this 1 1, this is written as this 1 1, and the second row 1 comma minus 1 is put into the second column. So if we started with this 1 1 notation and 1 comma minus 1, then we don't need to change the we don't need to make transpose. We just put those columns into two different columns. Okay, so this notation is better than the previous one. Okay, so if v which equal to x comma y belongs to R2, then what we can see that we are, so this is actually, in our case, this is transpose. This belongs to xy. This means this has some non-trivial solution. Means there exists C1 C2 belongs to the coefficient real number such that C1 V1 plus C2 V2 equal to x comma y, equal to the element v. Okay, so that is same as saying the equation star has a solution. equation star has a solution. Let us check if it has some solution or not. So again, C1 V1, this combination, we can write this combination as this, and another, now there we are considering some V instead of 0. So here we will write the value of V, which is x comma y. Okay, so we simply choose, instead of the coefficient matrix A, we choose A comma this V. Okay, A comma this, we should write the coordinate, but it is okay. Let us write the coefficient matrix, augmented matrix. Previously it was coefficient matrix. Now we'll write augmented matrix. Augmented matrix means A together with the coordinate of V, which is denoted by some B. Okay, so in our case it will look like the coefficients are 1 1, this one, and 1 minus 1, and the augmented, the right hand side will be the V, x comma y. So again we perform the same operation like this. So first r1 plus r2, this will give me, so I am saying we are changing r1 to this r1 plus r2. Okay, so 1 1 1 0, sorry 2 0, and x plus y, 1 minus 1 y. Now half of r1, so it is 1 0 x plus y by 2, 1 minus 1 y. Now also we simultaneously I was doing minus times minus 1 times r2, so it is minus 1 plus y minus y. Now r2 plus r1, so 1 0 x plus y by 2 and 0 1 minus y plus this, so it is x minus y by 2. So from here it is clear the equation has solution. The equation star has solution. Star has a solution. So what is the solution? The solution is the last, this part. Sorry. Okay. This one will be the solution. Right. So we can write x comma y, this as x plus y by 2 times 1 comma minus 1 1 1 plus x minus y by 2 times 1 comma minus 1. This is actually nothing but the vector v1, this is vector v2. So any element can be written as linear combination of v1 v2. So from here it is clear that the set S, which is v1 comma v2, spans v. Therefore v S is a basis for v, and the number of element in the basis, in this basis, called dimension of v. So in this case S has only two elements, v1 v2, so dimension of this v or r2, dimension of v is 2. So let us state explicitly dimension, let V equal to the vector space V as a basis B, then dimension of V is nothing but the number of vectors in B. Okay, for example, here in the set S there are only 2 elements, so dimension of V will be 2, right? So this is how the dimension is defined. Now note that there are different bases, so instead of choosing the E1 E2, the most easiest basis, we can choose this also. So what we have seen, this E1 plus E2 and E1 minus E2, which is these two also a basis. This is nothing but rotation of XY axis. We have only rotated 45 degrees. So this is also a new basis. But note that the dimension is not changed. So dimension with respect to this basis, this, if we consider this basis, then the dimension is 2. So, and if we consider E1, E2, the dimension is also 2. So the dimension is independent of chosen basis. This is one important fact. And there are some properties, some replacement lemmas, from which you can prove that basis is same as maximal linearly independent set, and it is also minimal spanning set. So what is the meaning of this? It means if some V1, V2, V3, those are linearly independent, okay, and this is maximal linearly independent set. It means if we add another any vector V, then that will make it linearly dependent set. So this is the meaning of maximal. In this case, the dimension will be 3. Okay. Similarly, minimal spanning set gives a basis. So if we delete one element from the spanning set, then that will not form a basis. Okay. So let us solve question number 1. There are 4 vectors, and alpha 1, alpha 2, those are 4 rows of 4 by 4 matrices A. Then which of the following elements belongs to the row space? So let us see. First, we put those vectors in the rows of the matrix A. Alpha 1, alpha 2, alpha 3, alpha 4. Those are rows. So that is same as saying 1, minus 1, 0, 1, 2, 2, minus 2, 2, 4, 6, minus 3, 3, 0, minus 2, minus 6, 1, minus 1, minus 2, 1, 0. So this is the rows. Now we perform the operation row reduction. So R2 we subtract 2 times R1 from R2, so that the first non-zero entry vanishes, because R1 already contains some non-zero entries, and moreover this is 1, So we just subtract the first row, all the others row, applying some coefficient. So we are doing the operation R2 minus 2R1. Okay, it is first row is unexchanged, is fixed. Now 2 get cancelled, 2 minus 2 which is 0, and similarly all the others entries will be like this. So second entry is also vanishes, 0 0, then 2 2 and 2, then 0 0 0 1 0. Again we are doing R3 minus plus 3 times R1, and another operation is R4 minus, because we want to cancel this one, so subtract R1 from R4. So R4 minus R1, this will give me 0 0 minus 2 0 minus 2. Okay, so now again we'll perform another operation, half of R2. So everything is same, those rows are same, but we are only scaling the second row, 0 0 1 1 1, and all the other rows are same. Then after this, let us perform okay. So R4 minus plus 2R2. Again we want to subtract this, we want to remove this minus 2 in the fourth row. So all those others rows remain same. We can copy paste all the others rows. Copy. No. Only the third last rows will be changed. Sorry, the second row I have changed here, so it is 1 1 1, and the last row will be 0 0, then minus 2 plus 2 which is 0, and then 2, and again 0. So this is what the last row will look like. Okay, now again we'll perform another operation. So now what we can do, so those are my pivot entries, this one, or leading entries, leading non-zero entries. Now we can perform this. So we want to remove all those non-zero entries from this third column because it contains the leading non-zero entry. So let us perform the operations. R1 minus 3 minus R, yes, R1 minus R3 and R2 minus R3, then R4 minus 2R3. So R4 minus 2R3 will give me 0. So it is 1 minus 1 0 0 2 0 0 1 0 1 0 0 0 1 0 0 0 0 1 0. So this is the row reduced echelon form, RREA. Let us denote it by R. R say. Now we need to see which of the following elements belongs to the span of rows. That is, we need to see if x, x1, x2, x3, x4, x5, this belongs to span of R1, R2, R3 and R4. There are 4 rows. So sorry, rows are denoted here by alphas. So span of alphas, alpha 1, alpha 2, alpha 3, alpha 4. But note that what I have done is row reduction, and we know that if a matrix is reduced to its row echelon form, then span of all those elements is same as span of R, span of the new rows. So that means that x1, x2, x3, this vector, this belongs to span of these new rows. But here it is easy to see what the span of the new rows will look like. So if we multiply x1 with the first row, multiply the first row with x1, there are only 3 non-zero rows. Sorry, that element also will be 0. This is, I have not changed. So there are only 3 non-zero rows, and it is easy to see what is the span of those 3 rows. So span of the 3 rows, it will be x1 times 1 minus 1 0 0 2 plus x2 times 0 0 1 0 1. Instead of x2, let me write x3 because it appears in third column, so that the main objective is to match those indices. So it appears in third column, so I am writing span of writing x3 times the second row plus x4 times 0 0 0 1 0. Okay, so this is same as x1. There is no other element, comma, minus x1, x3 times 0 equal to 0, x4 times 0 equal to 0. Then x1 times 0 is 0, x3 times 1, so it is x3, x4 times 0 0. Then there will be x4 because only 4 will survive, and then there is 2x1 plus x3. So if this x1 up to x5 belong to span of this, then x2 must be same as the second component, must be same as negative of the first component, and the fifth component x5 is same as 2x1 plus x3. Okay, so this is how we can see if something belongs to span of those sets or not. So let us see the answer. So the second component should be negative of the first component. So if this belongs to this span, then the second component should be the negative of the first component, as we have seen. This is 1. So which is not true for A, option A, right? So this will imply 0 should be same as minus 1 times the first component, which is 1. So 0 not equal to minus 1. So this is okay. This element does not belongs to span by first condition. Now B I need to check. For C, D I need to check, because for B, C, D the second component is minus 1 times first component. Now let us check the condition 2. x5 will be 2x1 plus x3. So what is 2x1 plus x3? 2 times 1 plus x3 is third component, which is 2. 4. So here all those conditions are satisfied. So B is an answer. Now let us check the second one. So we will check 2x1 plus x3 equal to x5. 2x1 plus x3 equal to x5. We'll check this condition. So for C, 2 times minus 1 plus x3, which is 1, equal to minus 1, which is non-zero, not equal to x5. Sorry, x5 is 2 in this case. So C is not true. A is previously not true. And similarly, it is easy to see that D is also not true. In this case also, minus 2 plus 3, which is 1, not equal to 2. So only B is the correct option. Okay, in this way, we can check, instead of considering all those vectors, we can check for any given vectors if a new vector belongs to the span of those vectors or not. Now question number 2. Which of the following set can be considered as basis of row space of A? So let us see what is the okay. Let me copy this. So we have seen that this row reduced echelon form, this is nothing but it is obtained by some elementary row operation, elementary row operations. So by this we can say that row space of A, row space means linear, all those vectors formed by linear combination of rows of A. So row space of A is same as row space of, this is R, say, of R. All those are not copied, 1, 2, 3. And moreover, the non-zero rows forms a basis for non-zero rows of row reduced echelon form, forms a basis for A, row space of A. Okay. So from here we can say that those are bases 1, -1, 0, 1, 2, 0, 0, 2. Sorry, those will be 0. I don't know from where I have copied. So this is the only one. Okay. This. This I should copy this one. 2, 1, 0, 0, 0. 2, 1, 0. So this is the row reduced echelon form of A. So the first row is 1, -1, 0, 0, 2. The second row is 0, 0, 1, 0, 1. The third row is 0, 0, 0, 1, 0. So this is a basis, and this is a basis for the row space. So from here it is clear that dimension of the row space is 3 equal to rank. Dimension of row space equal to rank of A. And what is rank? Rank is number of non-zeros zero rows in the row reduced echelon form. So rank should be 3. So dimension of row space will be 3. But in this case dimensions are 2, because if those are bases, sorry, not D, C. If those are bases, then there are only dimensions should be 2. There are only 2 vectors in the set 1, in the set 3. So the possible option should be either B or D. But note that B is already a basis. Sorry, D, because all those entries matches. This is V1, this is our V2, and this is V3. But let us see if this is also a basis or not. So this is not a basis, because we can see if we choose this entry, then what happens? We have seen that this entry, this vector cannot belongs to the row space, because that vector does not satisfy this relation. 2x1 plus x3 should be x5. So in this case, if we consider this element, x1 is 0, x3 is 0, 2 times 0 plus x3, which is 0, equal to 0. This is not same as x5, right? So this does not belongs to the space A. So this cannot belongs to the row space. So there is no possibility of the basis. Bases are taken from the row space. If that vector itself does not belongs to the vector space, then that cannot be basis. Because what is the definition of basis? It is a linearly independent set from the vector space, and it also span the vector space. So it is not even a linear, it is not even a subset of V. So it cannot be a basis. So B is also false. And from here it is clear that option D is correct. Question number 3. So we need to find coordinate matrix of this vector in row space of B, row space of A. Okay, let us see what is the row space. with respect to the basis, ordered basis obtained in Q2. So in Q2 we have seen this is the correct ordered basis. Option D, which is same as this. So let me say what is the definition of coordinate. Let V be a vector from the vector space capital V, and V1, V2 up to Vn is a basis. This be a basis. Then coordinate of V, this is denoted by V with respect to this basis. So let me denote the basis by this B. So coordinate of V with respect to basis B. Coordinate of V with respect to the ordered basis. So we must not change the order. So rearrangement is not allowed. The ordered basis B. It is same as, so let this be a basis such that V equal to this combination C1 times V1 plus C2 times V2 up to Cn times Vn. Then the coordinate, it is denoted by this uh, C1, C2 up to Cn. So we put all those coefficients in a column. Okay. So we need to see coordinate of this B1 minus B1 up to this with respect to the basis this. So let me copy the basis entries. So this is the ordered basis. This is the ordered basis. This is V1, V2 and V3 say. Then we can see that B1, minus B1, B3, B4, 2B1 plus B3. This is nothing but first V1 and then plus V2 and plus this V3. Right? Clear? It is clear that if we add those three vectors, that will give me this. Sorry, this is not the thing. I should say B1 times V1 and B3 times V2 and B3 times V3. So multiply the first thing with B1, then B3, then B4. Sorry, B1, B3 and B4. That will give me this element, right? Or you can directly check. How can we check? Let us directly check instead of assuming this. So let some C1 times V1 plus C2 times V2 plus C3 times V3 equal to this vector. Then this is nothing but C1 times V1, then C2 times V2 means 0, 0. Then C2, sorry, C1, then minus C1. And then C2 times V2, which is C2. Other entries are 0, so I am not adding. Now C3 times V3 means there will be C3 terms, and there is also 2 C1 corresponding to C1 V1 and 2 C2, and there is 0 times C3, so I am not adding. So So from here, if we compare, it is clear that C1 is same as B1 and C2 is same as B4. Sorry, C2 is same as B3 and C3 is same as B4. So those coefficient, therefore the coordinate of this vector V, let me denote it by V, coordinate of V with respect to the basis B, it is given by C1, C2, C3 in the matrices, in the column matrix. So B1, B3, B4. The correct answer will be this B1, B3, B4, but we should put it in a column. So B1, then B3, then B4. Okay. So we need to say, we are again considering the same question as question 1, and we need to see which which of the following sets can be considered as a basis of the solution space A times x equal to 0. So let us see which should span, which set spans the solution space. So in this case, if there is this kind of problem, again we start with A and we'll make row reduction. Okay. So what is the row reduced thing? Row reduced is same as row reduced echelon form is same as this. So you need to perform all those operations again if it is not previously. So this will be the row reduced echelon form. I have denoted it by R. Now we need to see the solution space. So to find solution space, we just first we mark the pivot columns. In this case, pivot column means the leading non-zero, the columns which contains leading non-zero entries. So in this case, this is pivot column. It contains non-zero entries, leading non-zero entries of the first row. It contains leading non-zero entries of the second row. It contains leading non-zero entries of the third row. So those are our pivot columns. Instead of denoting by same color, let me denote by different colors. Okay. Now what we can do, let us see what will be the solution of this. So those are called pivot columns. Pivot column, this notation is given in Gilbert's frame. You can look at that definition. This is not needed, but let us see how to solve the procedure. So those are pivot columns, and those are actually free. There are two free columns. This and this one are free columns. So the easiest way to get a solution is just put. So let us see which will be pivot and which will be free. The first entry, this will be given by the free column, corresponding to the free column. Then second, I don't know. Second is free column, and third will be correspond to the pivot column, and there is another fourth, and there is something else. Similarly, for another free entries, free column, I can choose any combination. So I'll draw the same thing again. This. So there will be two solutions because there are two free columns, or we can say in this way also. So rank of this is 3. Therefore, number of linearly independent solution, suppose this is m cross n, independent solution of x equal to 0, it is n minus r, right? In our case, this is 4 by 5 matrix. So 5 minus rank. So rank corresponds to these 3 independent columns. So other columns are dependent, linearly dependent. Okay. So we can choose freely. The linear combination of those other free columns we can choose freely. And let us choose the combination. So in the place of free column, we just put the combination 1 0 and 0 1. So here we put 1 0 and 0 1, because 1 0 comma 0 1, those are basis for R2, right? So in that analogy we put those two elements. Now what will be the solution of the for other places? So what from if we consider the first solution, then see that second place contains 1, and all the other second place and contains 1, fifth place contains 0. So if we consider the first row, then what will be the solution? X1 times 1 plus minus 1 times the second row, which is second row will be 0, minus 1 times 1, sorry, there is 1, minus 1 times 1, and then 0 times something. So 0 times something is always 0. Then 0 times another green, which is again 0, and then 2 times 0, which is 0. So this becomes 0. Therefore x1 equal to plus 1. Similarly, if we consider the second row, then note that for the second row, this is 1 times the third place, which is sorry, okay, 1 times the third place, which is x3. I don't know what is the value of x3, plus this times the 0 equal to 0. So x3 should be 0 because the coefficient of this entry is 0. So this is 0. Now consider the second one, the third row. So 1 times x4 I don't know, should be same as 0 because 0 times 0 is 0. So 1 times x4. So I am doing this r times x. So I am solving r times x equal to 0. So let me write explicitly because it may confuse you. So what is the value of r times x? So we have already observed x equal to 0 is same as, this is same as r times x equal to 0. But if we multiply rx, then rx is same as x1 minus x2 plus 2x5 equal to 0, the first row. The second row is x3 plus x5, then x4, then fifth row has nothing, so fourth row has nothing. This is 0 equal to 0 0 0 0. So I have chosen the value of x2 is 1 and value of x5 equal to 0. From here I am getting this is minus 1. Sorry, this should be minus 1. x1 minus x2, which is 1, equal to 0. And x3 plus x5 is 0, so I will get 0 here. Now x4 should be same as 0. Now what happens if we choose x2 equal to 0 and x5 equal to 1? We can choose those two things freely. So I am choosing this. What will we get? We get x1 equal to minus 2x5, so minus 2. And if we choose those two things, then x3 equal to minus x5, which is minus 1, and x4 equal to 0. So another solution will be minus 2, then 0, then minus 1, x3, and then x4 equal to 0. So those two will be a solution for x equal to 0. Okay, so already written in transpose, that's why they have written in rows. Minus 1 1 and 0 0 0, and the second one is minus 2 0. Okay, minus 2 0, minus 1 0 1. Some network issue, so let me switch on the camera. Sorry, the if we choose 1 0, I have calculated wrongly in this case. So this corresponding to this. Let me again choosing x2 equal to 1, x5 equal to 0, which will give me this. So if we choose this, then what will happen? x1 minus 1 plus 2x5, which is 0, equal to 0. That means x1 equal to 1. So previous answer was correct. It should be plus 1. Okay. And then similarly x3 plus x5, x3 plus 0 equal to 0. So x3 equal to 0 and x4 is 0 already. Okay. So this should be the correct answer, right? 1 1 0 0 0 and minus 2 0 minus 1 0 1. And you can see that others will not be a basis, right? Basis of the solution space. Why the other sets are not basis? Because let us check the first one, the why a is not a basis. So if we multiply 1 1 minus 1, if we choose the if we multiply 1 1 minus 1 0 0, so what will be the answer? it will give me 1 1 minus 1. So the first thing is 0, it is okay, but okay, then the second, it will give me 0 here, and then 0 0 1, so it will give me 1 here, 0 0 1 minus 1 here. So this is non-zero because the second row will be minus 1. So this element does not even belongs to the solution, so this will not be a part of a basis. Similarly, you can show that C and D, those two are also not a basis. Okay, so this is how we can say. Consider A from the question 1 and let x equal to this, y equal to this vector. Then the system x equal to y, it admits a solution provided which condition. So we know arbitrary system does not necessarily have a solution. For example, suppose consider this equation x equal to 2 and x equal to 3. So it is not possible to have a solution of this simultaneous equation. Though this is linear, but this does not have solution. X cannot be simultaneously 2 and 3. So in this case, we need to find a condition for this for this x1 x2 up to x5 such that ax equal to y has a solution. Okay, so again we form an augmented matrix A and Y, where Y is taken from the uh, equation X equal to Y, and we'll see what the row reduction of this augmented matrix is. So we have previously done the computation, so let me copy it. Copy. What is happening? So in this case, we put an extra column y1 up to y5, y4, y1, y2, y3, and y4. This is the augmented matrix. And now we will perform row reduction. So R2 minus 2 R1, first one will give me y1 is constant, so y2 minus 2y1. Then r3 plus 3r1, so y3 plus 3y1. Then r4 minus r1, so it is y4 minus y1. Now again we need to extend this. So y1 is fixed. This is y2 minus 2y1 by 2, and then other are fixed, y3 plus 3y1, and the fourth row will be y4 minus y1. Those are fixed. Only second rows are stretched by half, by the factor half. And now r4 plus 2r1. So again we need to add an extra column. So all those are fixed, only r4 is changed. y3 plus 3y1. Now r4 is same as y4 minus y1 plus 2 times r2. The element corresponding to r2 is y2 minus 2y1 by 2. So 2 times y2 minus 2y1 by 2. So 2 are cancelled. So it becomes y4 plus y4 minus 3y1 plus y2 plus y2. Okay. And finally there are lots of operations. So we do all the operations. For example, what is y r1 minus r3? So it means y1 minus r3 means the third, which is y3 plus 3y1. So it is y1 minus y3 plus 3y1. Similarly, what is r2 minus r3? So if we subtract r2, if we do the operation r2 minus r3, this will give me sorry for the disturbance. There are some network issues with my laptop. So let us complete it. The third row will be y3 plus 3y1, an extra element. Now the last one will be minus 9y1 plus y2 minus 2y3 plus y4. y4. This one. But note that the last row in the left hand side is 0. Okay. And in the right hand side, the last row is non-zero. Last row has some expression. Therefore, ax equal to y is same as rx equal to the y dash. So this, let me denote it by r comma y dash. So x equal to y, this is if and only if this. But rx equal to y dash, this has a solution if and only if rank of the matrix R is same as rank of the augmented R comma y dash, rank of the augmented matrix. So this implies the last row. So rank of this matrix is 3. There are 3 non-zero rows, but If this is 0, then rank becomes same, but if it is non-zero, then rank differs. Rank of the extra thing becomes 4. Therefore it has solution if and only if the last corner entry should vanishes. This must vanishes. So in this case, minus 9y1 plus y2 minus 2y3 plus y4 must be 0. And let us see what is the corresponding to. So we need to write in terms of y2 in terms of other thing. So this is eternally y2 equal to plus 9y1 plus 2y3 minus y4. So this is the correct answer. Okay. So we have nothing but perform some row reduction, and finally this is the key fact what we have used in this case. Rx has solution if and only rank of R is same as rank of the augmented matrix. Okay. In this question, the vector space V is 2 by 2, say the space of all 2 by 2 matrices, and we need to see the subspace. We need to consider the subspace W1, W2. So we need to compute the dimension of W1, W2. First, note that any element of W1 x1, take an element from W1, x1, x2, x3 minus x3. This belongs to W1. This can be written as x1 times 1 0 0 0 plus x2 times 0 1 0 0, because those are entry wise multiplication, scalar multiplication, and x3 times 0 0 1 and minus 1. And let me denote those entries as some these entries as some alpha or some vector v. Let me denote it by v1. This is v2 and this is v3. So we see that any element belongs to the span of this v1, v2, v3, right? So w1, this belongs to span of v1, v2, v3. Therefore w1 is a subspace of this spanning set. And moreover, not a subspace, w1 is actually equal to spanning set of this v1, v2, v3. because see that v1 is also belongs to this w1, right? So from the first observation, what we are getting, w1 is a spanning set of this, but also v1 belongs to v1 equal to 1 0 0 0. This is also belongs to w1, because w1, what is the condition for staying in w1? The third entry and the fourth entry will be negative of each other, which is satisfied by 0 0, right? So similarly, v2, v3 belongs to w1, because what is v3? Here the fourth entry is same as negative of the third entry, so those also belongs to w2, w3. Therefore, take any linear combination, because w1 is a vector space, span of this v1, v2, v3 also belongs to also contains in W1. In the other word, span of, therefore, from those two things, those two inclusions, span of V1, V2, V3 equal to W1. Now, if we can prove W1, W2, W3 are linearly independent, we are done. Then that, V1, V2, V3 are linearly independent. Then, by the definition of basis, this is a basis. The set V1, V2, V3 is a basis. So we'll try to prove it. So let C1, V1, C2, V2 plus C3, V3 equal to 0. Then we have already know what is the combination C1, V1, C2, V2, C3, V3. This combination is nothing but just replace x1, x2, x3 by C1, C2, C3. So it is C1, C2, C3 minus C3. So this is 0, 0, 0, 0. But 0 means component wise 0. So C1 should be 0, C2 should be 0, and C3 is also 0. Therefore, V1, V2, V3 are or it is a linearly independent set. Linearly independent set. Therefore, so let me denote it by S. Say S is a basis for W1. Okay, so S has three elements, three vectors. Therefore, dimension of S equal to 3. So we will similarly we can prove that dimension of W2 is 2, because what is the generator of W2? W2 contains element of the form y1, y2, y2, y1. So W1, sorry, W2 contains element of the form y1, y2, y2, y1. Note that those are actually symmetric matrices, right? And these always can be written as y1 times 1, 1, 0, 0 plus y2 times 1, 1 in the diagonal, 0, 0. So from here, by similar argument, we can prove that those two elements span this W2, and those two are linearly independent. This also should be clear by the same kind of for your, if you want to convince yourself, just check by this kind of combination. So let me denote this by some V1 dash, and this is V2 dash. Okay, so V1 dash V2 dash is a basis. The set S dash is a basis for W2. So dimension of W2 equal to 2. This is not S. Dimension is always for a vector space W1 corresponding to the basis Okay, so now we need to see the intersection. Let ABCD, this vector, belongs to the intersection. Or instead of ABCD, let me write x1 1 notation, x11 12 x21 x22 belongs to the intersection. That means this will belongs to W1. Unstable internet. Okay, let me complete this example. So the first one will imply those two will be belongs to W1. So by what is the definition of W1? Those two entries are negative of each other. So let A equal to this belongs to W1. Since A belongs to W1, then the second x22, that entry will be same as negative of x21. And since A belongs to W2, there will be other relations. What will be the relations? The extra relations. A belongs to W2. W2 means the set of symmetric matrices. So, is it the only symmetry? Not only symmetry, the diagonal are okay. Symmetry means we are flipping along the diagonal, but instead of symmetry, there is another extra condition, that is flipping along both diagonals give me the same thing. Not only symmetry, there is more extra things. Diagonal are same. Okay, so something belongs to W2, so that will give me other extra two conditions. So the diagonal entries are same, both the diagonal. X11 is same as x22, and the reverse diagonal, which is x12, this is same as x21. This is condition 2, this is condition 3. Now note that those, so what will be the, note that we can reduce condition. Okay, so let me put it as linear combination of equations. The second equation give me x11 plus 0 times x12 plus 0 times x21 minus 1 times x22 equal to 0. Okay. You can do in this way, otherwise another method is also there. We can directly also argue, because from here it is easy to see what is happening. X22 is same as minus x21, but x21 is same as x12. So from 1 and 3, from 1 comma 3, x22 is same as minus x21, and x21 is same as x12. So minus x12. Okay, and there is another equation which is independent, because 1122, no, x22 is same as x11. So from 4 there is another relation. You can put all those relations together. X11 is same as x22. So all those entries are related by each other, related to each other. Therefore, the intersection W1 intersection W2, this is actually given by this set. So all those entries, let me denote it by K. All those are same. So first one is x11, which is K. Then x12, 1/2th element is minus K. And x21, which is again minus K. X22 is K. such that k belongs to real number, right? So this is the intersection. So it is clear that all those entries are actually generated by k. All those entries can be written as k times 1 1 minus 1 1. Therefore, it is spanned by the single element, and this single entry is non-zero, therefore linearly independent. So it forms a basis. So the vector, let me denote it by v. Then s equal to v. This is a basis for the intersection W1 intersection W. Okay. Therefore, dimension of dimension of the intersection W1 intersection W2, we are considering this basis, so that will be same as 1. And we know that dimension does not depend on a fixed basis. We can choose any other thing. So C is the correct option and D is obviously false. Okay, this is done. Which one is the correct statement? Superset of linearly independent set is linearly independent. So it may be true or it can be also false. Because why? In R2, consider this set E1, E2, the standard basis. Then if we take any superset of this set, that will become linearly independent, right? So superset may not be linearly independent. This can be independent, but it also can be dependent. If we, instead of S, if we choose S dash equal to E1, we can extend it further such that it remains linearly independent, because we can also add E2. But now we cannot extend further in R2. Whatever V, those two are linearly independent. But adding any extra element, that will become linearly dependent. This set, right? So this is false. Any set which contains linearly dependent set is linearly dependent. So any set which contains a linearly dependent set is linearly dependent. That is true, because suppose S dash, let S dash is same as S union some extra thing, S union some T, and S is linearly dependent. Then clearly S union T will also be a linearly dependent set. Why? Because we can write take some element. S is linearly dependent means there are some non-zero combination, non-trivial combination C1, some V1 up to Cn Vn equal to 0, such that all of Ci, sum of Ci is non-zero for some I. Then we can choose the same combination, right? We can again choose the same combination for S union T. If T has some extra element, we can put 0 as coefficient to those elements. So if S is linearly dependent, then its superset must be linearly dependent. So 2 is true. Any set which contains 0 vector is linearly independent. That is completely wrong, because in the first in the earlier discussion we have seen that if something contains 0, then that must be linearly dependent, because it admits some. So let v equal to 0, then C times V, 1 times V equal to 0. And this is a non-trivial combination. The coefficient 1 is non-zero, right? So there are some non-trivial combination, linear combination, which give me 0. So if a set contains 0 vector, or 3, if a set contains 0 vector, then it must be dependent. Any subset of linearly dependent set is linearly dependent. Again, 4 is not true, because the vector space V is linearly dependent. V equal to R2 is linearly dependent, but its subspace E1, E2, the set, its subset is linearly independent. Okay, so in this question, you need to find the coordinate of 6 to 6. So again, the same kind of method you can use. Just put those 1 0 minus 1, those things as columns. 1 0 minus 1, 1 2 1, 0 3 minus 3 2 as a column. So we just write the augmented matrix A B. Suppose this is B, the vector B. Means B is not exactly that vector, but the transpose of 6 to 6. So we put all those things as column. B equal to 6 transpose of 6 to 6. And just row reduce it. Then we will get the solution. In this case, I know what should be the solution. Let me say the answer. In this case, you can check that the correct solution will be C. Answer will be C. You can check it. Is it important for um, exchange of matrices? So you should do it. So let me complete this discussion here. So we'll again meet in the next week. Thank you for your attention.